Unveiling the mysteries of the universe, from the Big Bang to its ultimate fate. The Big Bang and the origin of the universe. Introduction to the concept of the Big Bang as the prevailing theory for the origin of the universe. Explanation of the singularity and the cosmic expansion that initiated the universe's existence. Overview of the significance and impact of the Big Bang theory in cosmology. Introduction to the concept of the Big Bang as the prevailing theory for the origin of the universe. The Big Bang is a widely accepted scientific theory that explains how the universe began. It suggests that the universe started from a very hot and dense state called a singularity. The singularity contained all the matter and energy that would later form the universe. About 13.8 billion years ago, the singularity began to rapidly expand, and this event is known as the Big Bang. As the universe expanded, it cooled down, allowing the formation of galaxies, stars, and planets. The Big Bang theory is supported by various pieces of evidence, such as the cosmic microwave background radiation and the observed redshift of distant galaxies. It is important to note that the Big Bang theory doesn't explain what caused the singularity or what happened before it, as those remain open questions in science. Scientists continue to study and explore the Big Bang theory to better understand the origin and evolution of our universe. Explanation of the singularity and the cosmic expansion that initiated the universe's existence. The singularity is a term used to describe the extremely hot and dense state at the beginning of the universe. It was a tiny point where all matter, energy, space, and time were squeezed into a very small space. The singularity existed before the Big Bang and is where the universe originated from. The Big Bang happened when the singularity suddenly started expanding rapidly. This expansion caused the universe to grow and spread out over time. As the universe expanded, it became less dense and cooler. The expansion of the universe continues even today. The cosmic expansion led to the formation of galaxies, stars, planets, and other celestial objects. The singularity and the subsequent cosmic expansion are key components of the Big Bang theory, explaining how the universe came into existence and how it has evolved over billions of years. Overview of the significance and impact of the Big Bang theory in cosmology. The Big Bang theory is of immense significance in cosmology as it provides a framework for understanding the origin and evolution of the universe. It is the prevailing scientific explanation for how the universe began and has been widely supported by observational evidence. The theory has revolutionized our understanding of the cosmos and has had a profound impact on various fields of science. By studying the Big Bang, scientists can delve into the fundamental nature of space, time, matter, and energy. It has allowed us to trace back the history of the universe and gain insights into its early stages. The Big Bang theory has helped explain the formation of galaxies, stars, and other cosmic structures, providing a deeper understanding of their properties and evolution. It has provided a basis for understanding the distribution of matter and the large-scale structure of the universe. The theory has facilitated the prediction and discovery of phenomena such as the cosmic microwave background radiation, confirming its validity. Moreover, the Big Bang theory has stimulated further research and investigation, leading to the development of new theories and concepts in cosmology. It continues to inspire scientists to explore unanswered questions about the universe, such as the nature of dark matter and dark energy. Overall, the Big Bang theory has had a transformative impact on our understanding of the cosmos, shaping the field of cosmology and driving scientific progress in unraveling the mysteries of the universe. Processes and events of the Big Bang. Cosmic inflation. Discussing the rapid expansion of the universe during the inflationary period. Nucleosynthesis. Explaining the formation of light elements, such as hydrogen and helium, during the early stages of the universe. Recombination and the CMB. Describing the release of cosmic microwave background radiation and its significance as a remnant of the early universe. Cosmic inflation. Discussing the rapid expansion of the universe during the inflationary period. Cosmic inflation refers to a period of extremely rapid expansion that is believed to have occurred in the early moments of the universe, shortly after the Big Bang. During this inflationary period, the universe expanded exponentially, stretching space itself. The concept of cosmic inflation was proposed to explain certain observations and features of the universe that the Big Bang theory alone couldn't account for. It helps address questions related to the large-scale structure and uniformity of the universe. The rapid expansion of cosmic inflation caused regions of the universe that were originally in close proximity to become much farther apart. This expansion smoothed out irregularities and made the universe remarkably homogeneous on a large scale, explaining why the universe appears so uniform in temperature and density. Cosmic inflation also provided a mechanism for the creation of the initial fluctuations in the density of matter, which later led to the formation of galaxies and other structures. The evidence for cosmic inflation includes the observed isotropy, uniformity, of the cosmic microwave background radiation and the distribution of galaxies. It is important to note that cosmic inflation is a theory that helps explain certain features of the universe, but the exact details of how it occurred and what caused it are still the subject of ongoing scientific research. Nucleosynthesis, explaining the formation of light elements, such as hydrogen and helium, during the early stages of the universe. Nucleosynthesis refers to the process of creating new atomic nuclei, the central building blocks of elements, in the early stages of the universe. During the initial moments after the Big Bang, the universe was extremely hot and dense. The conditions were favorable for nuclear reactions to occur. The primary elements that formed during nucleosynthesis were hydrogen and helium, along with trace amounts of lithium and beryllium. The formation of these light elements occurred through a series of nuclear fusion reactions. In the first few minutes after the Big Bang, temperatures were incredibly high, allowing protons, hydrogen nuclei, and neutrons to collide and combine to form helium. This process, known as primordial nucleosynthesis or Big Bang nucleosynthesis, was responsible for the creation of about 75% hydrogen and 25% helium in the early universe. The abundance of these light elements can be precisely predicted by the Big Bang theory and is consistent with observational measurements. It is important to note that the synthesis of heavier elements, such as carbon, oxygen, and beyond, occurred later in the evolution of the universe through processes like stellar nucleosynthesis in the cores of stars. Nucleosynthesis, both during the early stages of the universe and in stellar interiors, played a fundamental role in shaping the elemental composition of the universe we observe today. Recombination and the CMB, describing the release of cosmic microwave background radiation and its significance as a remnant of the early universe. Recombination refers to a critical event that occurred approximately 380,000 years after the Big Bang, when the universe had cooled down enough for atoms to form. During the early stages of the universe, the intense heat prevented electrons and protons from combining to form stable atoms. However, as the universe expanded and cooled, the temperature dropped to a point where electrons could combine with protons to form neutral hydrogen atoms. This process of recombination marked the transition from an opaque plasma of charged particles to a transparent universe filled with neutral atoms. As a result of recombination, photons, particles of light, were able to travel freely through space without being frequently scattered by charged particles. These photons, which were released during recombination, have persisted throughout the history of the universe and can still be detected today. The cosmic microwave background, CMB, radiation is the remnant of these photons that were emitted during recombination. The CMB consists of extremely faint microwave radiation that permeates the entire universe in all directions. It is often described as the afterglow of the Big Bang, as it provides a snapshot of the early universe when it was just 380,000 years old. The discovery of the CMB in 1965 by Arno Penzias and Robert Wilson provided strong evidence in support of the Big Bang theory. The CMB has a nearly uniform temperature across the sky, with small variations that provide valuable insights into the structure and composition of the early universe. By studying the patterns and fluctuations in the CMB, scientists have gained valuable information about the age, geometry, and composition of the universe. The CMB is considered one of the most important pieces of evidence supporting the Big Bang theory and has been instrumental in our understanding of the universe's early history. Evidences supporting the Big Bang theory, cosmic microwave background radiation, CMB, highlighting the discovery and importance of CMB as a key evidence supporting the Big Bang theory. Redshift and Hubble's law, explaining the observed redshift of galaxies and the relationship between their distance and velocity. Abundance of light elements, showcasing the alignment between the predicted and observed abundances of light elements. Cosmic microwave background radiation, CMB, highlighting the discovery and importance of CMB as a key evidence supporting the Big Bang theory. The cosmic microwave background, CMB, radiation is a faint, uniform radiation that fills the entire universe. The discovery of the CMB in 1965 by Arno Penzias and Robert Wilson was a monumental breakthrough in cosmology. They accidentally detected a persistent background noise that could not be attributed to any known source, and after careful analysis, they realized it was the CMB. The existence of the CMB was a crucial piece of evidence supporting the Big Bang theory. The CMB is considered the afterglow of the Big Bang, as it is composed of photons that were released about 380,000 years after the universe began. The CMB provides a snapshot of the early universe when it was still hot and dense. Its uniformity and isotropy, the same in all directions, are consistent with the predictions of the Big Bang theory. The temperature of the CMB is extremely uniform, varying by only a few parts in a million. Small fluctuations in the temperature of the CM, known as anisotropies, provide valuable information about the structure and composition of the early universe. These anisotropies have been studied in great detail and have led to precise measurements of cosmological parameters, such as the age of the universe and the amount of dark matter and dark energy. The CMB also supports the concept of cosmic inflation, as it exhibits a remarkable level of uniformity on large scales, which inflation can explain. The CMB has become a cornerstone of modern cosmology and has greatly contributed to our understanding of the origin, evolution, and composition of the universe. Redshift and Hubble's law, observations of redshift and the relationship between velocity and distance. Redshift refers to the phenomenon where light from distant objects, such as galaxies, appears shifted towards longer wavelengths, or redder, compared to when it was emitted. The observation of redshift played a crucial role in the development of the Big Bang theory and our understanding of the expanding universe. Redshift is a result of the Doppler effect, which occurs when a source of light moves away from an observer, causing the wavelengths to stretch. The greater the redshift, the faster the object is moving away from us. Edwin Hubble, an American astronomer, made significant contributions by measuring the redshifts of galaxies in the 1920s. Hubble's observations led to the formulation of Hubble's law, which states that the velocity at which a galaxy is moving away from us is directly proportional to its distance. This relationship between velocity and distance is often expressed as v equals hd, where v is the recessional velocity, h, Hubble constant, is the proportionality constant, and d is the distance to the galaxy. Hubble's law implies that the universe is expanding uniformly in all directions. The redshift observations in Hubble's law provided strong evidence for the Big Bang theory, as they supported the idea of an expanding universe that originated from a dense and hot state. Further advancements in observational techniques, such as the use of spectroscopy, have allowed for more precise measurements of redshifts and a better understanding of the relationship between velocity and distance. Redshift observations continue to play a crucial role in cosmology, helping scientists map the large-scale structure of the universe and providing insights into its expansion rate and evolution. Abundance of light elements, matching the predicted abundances of hydrogen and helium in the universe. The abundance of light elements, particularly hydrogen and helium, is an important piece of evidence supporting the Big Bang theory. According to the theory, during the early stages of the universe, the intense heat and high density allowed for nuclear reactions to occur and create these light elements. The Big Bang nucleosynthesis, which took place within the first few minutes after the Big Bang, was responsible for the formation of about 75% hydrogen and 25% helium. The precise predictions of the abundances of hydrogen and helium based on the Big Bang theory closely match the observed abundances in the universe. Scientists have conducted extensive observations and measurements to determine the elemental composition of the universe, and the agreement between the predicted and observed abundances of hydrogen and helium provides strong support for the Big Bang theory. The precise agreement between theory and observation adds significant credibility to the idea that the universe began with a hot, dense state and has been expanding and evolving over billions of years. It is important to note that while hydrogen and helium are the dominant elements, smaller amounts of other light elements, such as lithium and beryllium, were also formed during the Big Bang nucleosynthesis and have been observed in the universe. The successful prediction and matching of the abundances of light elements provide compelling evidence for the validity of the Big Bang theory and our understanding of the early universe. The ultimate fate of the universe. The Big Freeze, explanation of the scenario where the universe continues to expand and cool. The Big Freeze is a possible scenario for the ultimate fate of the universe if the expansion continues indefinitely and the cooling process persists. In this scenario, as the universe expands, the space between galaxies and cosmic structures increases, leading to a dilution of matter and energy. The expansion causes galaxies to move away from each other at ever-increasing speeds, making it difficult for them to interact and exchange matter or energy. Over an extremely long time scale, stars within galaxies would burn out, leaving behind remnants such as white dwarfs, neutron stars, and black holes. As the universe continues to expand, these remnants would become isolated, and no new stars would form. The universe would gradually become colder and darker as it becomes depleted of usable energy. Eventually, even black holes would slowly evaporate due to a process called Hawking radiation, contributing to the overall decline in energy. The Big Freeze scenario envisions a universe in a state of cosmic coldness and entropy, where the available energy is spread thinly and no significant cosmic processes occur. The ultimate fate of the universe as the Big Freeze is based on current understanding of the expansion rate and the behavior of matter and energy. It is important to note that the concept of the Big Freeze assumes that there are no significant unknown forces or phenomena that could alter the expansion or the fate of the universe. Further scientific discoveries and advancements may refine or alter our understanding of the ultimate fate of the universe in the future. The Big Crunch, describing the possibility of the universe collapsing upon itself due to gravity. The Big Crunch is a hypothetical scenario for the ultimate fate of the universe, which proposes that the expansion of the universe will eventually reverse and lead to a collapse. In this scenario, the force of gravity, which attracts matter towards each other, plays a dominant role. If the total amount of matter and energy in the universe is sufficient, it could counteract the expansion and eventually cause the universe to contract. As the universe continues to contract, galaxies, stars, and other cosmic structures would be pulled closer together under the influence of gravity. Eventually, the universe would reach a point of extreme density and temperature, resulting in a highly compressed state. The collapse would culminate in a singularity, similar to the initial state of the universe before the Big Bang. The Big Crunch scenario is analogous to the collapse of a rubber band when it is stretched and then released. However, it is important to note that the occurrence of a Big Crunch depends on the balance between the amount of matter and energy in the universe and the strength of gravity. Current observational data, including measurements of cosmic expansion and the distribution of matter, suggest that the universe may not contain enough matter to cause a Big Crunch. Instead, the evidence points towards a universe that is expanding at an accelerating rate, driven by a mysterious force called dark energy. Nevertheless, the possibility of a Big Crunch was once considered a potential fate for the universe based on the understanding of gravity and the available matter and energy. As scientific knowledge evolves, our understanding of the ultimate fate of the universe may continue to be refined and new possibilities may emerge. The Big Rip, discussing the idea of the universe tearing apart due to the accelerating expansion. The Big Rip is a theoretical scenario that suggests the universe will undergo an extreme fate known as cosmic tearing or the Big Rip. This scenario is based on the assumption that the expansion of the universe will continue to accelerate at an increasing rate. The driving force behind this accelerated expansion is believed to be a mysterious form of energy called dark energy, which is thought to permeate the fabric of space. As the universe expands and dark energy becomes more dominant, its repulsive effect on matter and energy becomes stronger. The Big Rip scenario suggests that the accelerating expansion will eventually become so powerful that it tears apart galaxies, stars, planets, and even subatomic particles. The accelerating force would overcome the gravitational pull holding cosmic structures together, leading to their disintegration. The universe would be subjected to an increasingly rapid expansion, stretching everything apart until even the fundamental particles that make up matter are torn apart. The exact timing of the Big Rip would depend on the properties of dark energy and its relationship with the expansion of the universe. It is important to note that the Big Rip scenario is highly speculative and based on current theoretical models, which may evolve as our understanding of dark energy and the dynamics of the universe improves. Observational data, such as measurements of cosmic acceleration and the behavior of dark energy, are continuously studied to investigate the likelihood of a Big Rip or alternative scenarios. The ultimate fate of the universe, including the possibility of a Big Rip, remains an active area of research and subject to ongoing scientific inquiry.